So in our agenda today, a few words about SolidCAD and flight software. Why should you be considering FluidFlow for your piping design software? And a few examples using the latest version of FluidFlow. If you have any questions, please type them into the chat window. We will reply to them by email later on. I know we have scheduled 30 minutes for this, but I'm going to try to keep it short and simple. Hopefully, you'll have enough to pique your interest and want to follow up on more detailed aspects of the tool. So SolidCAD, for those of you who do not know us, is a Canadian company, currently the first platinum partner of Autodesk and a member of Cancel group of companies, established in 1996 with a long history in the Autodesk channel. The largest technical team in Canada, and specialized in a number of industries, plant and process, manufacturing, AC, civil infrastructure, media and entertainment. We support and help our customers become more proficient using Autodesk and other tools through training, consulting, technical support, scan to BIM services, software development, product lifecycle management, and simulation and analysis. Offices across Canada, 15 at this moment, and 12 training facilities coast to coast. And as a part of Cancel Group, we have access to end-to-end solution from hardware to surveying equipment, laser scanning, GIS software, and CAD software. Some other tools that we are deeply involved with, FluidFlow, which is really the topic of today's first webinar, and other tools covering different industries. So we have partnered with Flight Software about 10 years ago. We're the Canadian distributors for FluidFlow. Flight Software is the developer of FluidFlow, a company formed in 1984. When first release of piping systems, FluidFlow, as the full name was known at that time. The company is an ISO 9001 2008 registered company. So in terms of software development, they do follow a set of very rigorous quality assurance procedures. It's headquartered in United Kingdom, in Northern Ireland, and while FluidFlow is the flagship product, it has and it is involved in custom software solutions for a number of companies like Fortis, British Columbia, Sterling Fluid Systems, Weir Group. Here's a snapshot of some of the customers from SpaceX, NASA, Dow, BASF, to Rio Tinto, Hyundai, and so on. The full list is available on that website. And a couple of testimonials from our own customers here in Canada, Texar Engineering in Sarnia and the Sudbury branch of Worley Parsons. Directly from users, they would tell you how FluidFlow as a solution the ease of use, the completeness, the accuracy are very important features that help them be successful in their piping design, and basically the software pays for itself from the first project. So let's talk a little bit about the different modules, and then a little bit in more detail about those, and we'll end with some examples. So latest version 346. A couple of important points here. The different modules are integrated in such a way that you actually use all of them on one flow sheet. So there's no need to save your network, export your network, import your network into another module. Everything happens in one single calculation flow sheet. Different modules currently include incompressible, so liquid calculations, gas calculations for compressible flows, settling and non-settling slurries and non-Newtonian liquids, two-phase gas liquid, as well as a dynamic analysis or a scripting module. So 5 different modules. Heat transfer, thermal transfer is automatically included with any of those, and you can get them in combination of any of these modules. So liquid or gas separately, two-phase would require liquid and gas. Non-Newtonian slurry would require liquid. And for scripting any of the previous modules. The software comes as a standalone license or a network license, and from an architecture standpoint is built around a number of databases, as you'll see, for liquids, solids, different components, pipes, and so on. Some important features and standout features, if you want, is of learn and use. The detailed quality assurance, you'll see a screenshot there from the different models that the software is shipped with, if you want to check for yourself. And something called automatic equipment sizing, which is going to be the topic of our next webinar in around mid-May. So let's look in a little bit more detail here. So incompressible flow, typically for liquids. Some of the important features here are going to be a quick plot of energy and hydraulic grade lines. So you can identify areas of potential problems in your network, especially in liquids flowing downhill, or potential negative static pressure or cavitation problems. The screenshot there, it's a composite pump curve when pumps are used in series or in parallel. I mentioned auto sizing of components as an important feature. So for piping, it's using the economic pipe sizing model or General equation. For pumps, the size for flow or size for pressure rise. Other components that could be auto-sized, valves, control valves, orifice plates, rupture discs. Viscosity correction based on Hydraulic Institute recommendations, and affinity law correction for impeller trimming also included. And in terms of applications, pretty much anything that requires liquid transport, cooling water systems, fire protection systems, mine dewatering, fuel, crude oil, lubricant systems, water transportation systems, desalination plants. So these are just a few applications. I'm sure you can think of some of your own where you could use this. The compressible flow module. The important part here is to recognize that FluidFlow
does not use an ideal gas approximation, but uses real gas conditions. So there are currently three equations of state built in. Benedict Webb-Rubin with Hans Starling modifications, Lee Kessler, and Peng Robinson. And this contributes to higher accuracy of results in a gas network. Some other options here that are going to be important, easily building gas mixtures by mole or mass percentage, detecting sonic choking in components, again, auto-sizing of components, ducts, fans, and compressors, safety release devices. Addition of heat transfer module allows us to look at the Joule-Thomson effect as well, and the plotting of composite fan curves for series and parallel fans is also important. And some applications as an example, application examples that our customers use FluidFlow for dust extraction systems, gas collections, natural gas supply feeds, and then transmission pipelines. Two-phase flow. Currently 8 available two-phase correlations. A highly accurate marching along the pipe solution algorithm for improved accuracy. Automatic flow pattern maps generated, one of which you are looking at right now. You can see the current flow regime on that selected component, stratified wavy. So all this is generated very fast. Real gas conditions for gas phase, as I mentioned previously, and some of the applications from liquefied natural gas processing facilities, flashing steam and water system, geothermal plants, cryogenic and ammonia systems, rocket propulsion systems. You probably noticed SpaceX and NASA's customers there in the previous slide, as well as in general petrochemical plant pipework. The next module, non-Newtonian and the slurry flow. Some important tools here that are going to help you in your design process. The ability to include pump derating due to solids. The ability to look at calculated solids delivered per unit time. The ability to find deposition velocities and consequently if blockage may occur in pipes. In general, operational issues and energy saving opportunities. Typical applications, mine tailing systems, hydro transport after combination processes of ore, wastewater and dredging, pulp and paper stock calculations also included. And we have quite a few customers in food processing industries that require shear thinning and shear thickening liquids, molasses, ketchup, you name it. So mayonnaise, yeah. So those are typical fluids in this industry that FluidFlow is being used successfully. And lastly, scripting or dynamic analysis. So this is a module that requires some programming skills. We're using Pascal and basic syntax here, languages to create macros that will allow us to tackle all sorts of problems. Basically anything that typically would be manual input or a manual change of boundary conditions, you could think of including in a macro. This way you can look at time dependencies in a system,
when boundary conditions vary, tank and fill and drain times, optimization of, let's say, a pumping station where you might want to find an optimum impeller or pump speed based on different pump properties and pump types. So in terms of outputs, you could get results in the graphical window inside FluidFlow, or export those results into Excel, create graphs in Excel. So quite flexible this way. Let's look at some examples in the software right now. And let me find my application here. Bring it over to the screen. There you go. So this is the interface of FluidFlow. Very clean and consistent. As I mentioned, one single flow sheet. Everything happens in this flow sheet, depending on the activated modules. So I'm going to click on the database pull-down menu here, and let's say database of pipes. You can see different pipe sizes, and obviously you can add your own. All these databases are customizable and also shareable in case you're using a network license. Different, let's say, pumps, right? Boosters and fans, pump curves defined here. Everything that entails data entry here has different ways to fit the curve. Again, depends on the type of data, and these databases are definitely important in terms of proper functioning of the software. About 1,300 fluids currently defined, so out of the box, and as I said, fully customizable. You can create your own fluid and your own mixture. If I'm to, let's say, filter through some, let's say, a simple Newtonian liquid, based on, let's just go here, based on the definition, you'll see in what kind of modules that fluid has enough information to be used in. So in this case, this kerosene, it's going to be used in a liquid-only application, while let's say a pure Newtonian fluid like ethanol, for example, has enough data that could be used in liquid, gas, and two-phase modules. Right. Here are some non-Newtonian liquids. I mentioned the food processing industry. Here's a mustard example, and viscosity law defined in this case as a power law. So you can see the viscosity dependency with shear rate. Okay. Solids database, that's going to be important in settling slurry definition. For example, here's a mica, a solid with the bulk density and solid shape factor value, so the deviation from a perfectly spherical particle. All these properties important for an accurate calculation. Okay, so again, from an interface standpoint, different tabs that will store different components here. So in terms of pipes, boundaries, so assigned pressure, assigned flows, reservoir, junctions, T, bands, Y, cross, or a generic connector. No resistance through this, but multiple pipes that could come in and out. Boosters, centrifugal pumps, PD pumps, fans and compressors, positive displacement pumps and compressors again. And valves, typical standard valve types, control valves, flow and pressure control, check valves, general resistances, so CV, CF, and so-called user-defined generic. So this is quite useful when you have a piece of equipment that, let's say, it's not present in the database, but you have actually catalog information about it, and you can define this way flow properties through relationships functions. Sign changes, reducer expanders, venturi tubes, orifices, relief devices, heat exchangers, shell and tube heat exchangers. So different component types, all available out of the box. No need to purchase extra databases of components. They all included with the software. So how do you typically operate? It's pretty straightforward. Start with a boundary condition here, and let's say start with a set of, for example, known pressures. I'm just going to throw maybe a couple of known pressure options here. Go back to pipes, and let's say I'm connecting these pressure nodes to pipes and end that with an open pipe. Connect this one with an existing pipe that adds a T junction right away. Very straightforward, easy to work with these. Right? So in terms of units, I could easily change from US Basic to SI. Properties, well, you've got length, you've got elevation on nodes, and the actual fluid. So let's, for example, create a quickly a mixing network here. So let's say ethanol at 1.7 atmosphere coming in here, maybe methanol. So right now I'm poking into the fluids database, right? Newtonian and non-Newtonian non-settling type, so not a slurry. Say maybe 1.5 atmosphere, and then let's say octanol, for example, at 1.5 as well. Now let's do something else. Maybe I'd like to know some information on screen, which I could also look at using the flyby like that. But I'm going to go and say select these pressure nodes and show some properties on flow sheet, like, for example, maybe elevation, maybe fluid, maybe pressure. There you go. And let's do a calculate, right? So we can see the flow direction easily, and also some messages here, high pipe velocity. So as I mentioned earlier, we're using an economic pipe sizing model by default using the General equation. So this is flagged as a warning because the calculated result right now, halt velocity on that pipe segment, which, by the way, its number is here, -1, right? Calculated velocity is 14 feet per second. Suggested economic velocity and an economic size about, let's say, 4 inches. Economic velocity at 4.2 feet per second. Okay? So too narrow pipe, too high velocity. By the way, these warnings, you actually can configure the limits on them. If I'm looking at liquid limits here, there you go. So what's considered too high pipe velocity, it's about 14 feet per second, right? So the calculated one is sorry, that let's say 12 feet per second. The calculated one is 14 out of range, hence the warning. So very straightforward to work with. Let's maybe jump into a couple of other examples here before we run out of time. So let's say, for example, here's a slurry network that goes at different elevations. All these nodes have a different elevation listed here. So if I'm going to hit calculate on that, so what do I have here? I have an input into the network of 45 cubic meters per hour of as a total flurry flow of water as carrier and mica as a solid defined by a weight percentage. I'm not using a size distribution data. I'm simply using D50 and D85 at these values. So what can I get from this? Well, I can get, let's say, on the outlet here, I can get solids delivered. So I'm looking at about just under 3 kilograms per second of solids delivered, a total flow. On a pipe, I'm looking at deposition velocity here, right? So all important information to see if I'm running the risk of a blockage or not. So out velocity calculated is 8 feet per second, deposition velocity of 5. So no risk of blockage. Or if we decrease the flow, let's say 25 cubic meters per second. Okay, and in this case here, what the message is saying to us is saltation or blockage may occur. Right? So now my out velocity 4.5 calculated 4.5 feet per second is very close here to the CVD deposition velocity. Right? It's just under it. So a warning that I may run the risk of blockage in the pipe, and a few more pipes of the same with the same warning. So a quick example of slurry transport. Let's look at this one here, 4 pumps in parallel. So we have these pumps right here, right, and the reservoir, and we're reservoir containing water, and we're transporting that some farther out and higher up. And if I am to show composite chart setup, let's say between these 3 boosters, 10, 11, and 13, these are the node numbers of the pumps. The composite chart looks like that. Okay, so you can see the duty point there. You can see the system curve and the individual booster curves. These are all identical pipes, so one single curve for that. Okay. Again, very useful information. And lastly, gonna jump into this as a scripting example. Okay, so let's say over a period of time we have some scaling happening in the pipe, so some deposition of material there that reduces the diameter, and would like to get an estimate on after how long we should schedule some maintenance, some cleanup, or maybe some replacement on some of these pipes. So let's look at the view scripting module right here. So this is script in basic language. You could also use Pascal, as I mentioned. And if I'm to, let's do a quick calculate, update the network, and then run the script here. So this will consider the variation in the the pressure drop due to scaling over an amount of time, and they will keep on updating that and give us an information on how the flow will be reduced over that amount of time, and when we should consider this as not suitable for service anymore. Too much scaling there. So I hope this has been interesting and useful as an introduction to the tool, and thank you all for joining us. Hope to see you again at the next webinar, equipment auto sizing, scheduled for May 14th. Thank you, and have a great day.